think, yeah, because we had a bit of a short break between the two sessions, people are going to need a few minutes to join in full. So, yeah, maybe a slow start and then people will catch up. So, it is again my pleasure to introduce Luca Selak, whom you've already known from yesterday, those of you who've attended his session on PLC programming. And today, Luca is sort of going to continue and show you what we do with our students in terms of robotic programming, especially within the courses on industrial automation and related ones. So, Luca, please. Sorry, I cannot hear you. I think there seems to be a problem with the microphone. Don't worry. No, I can't hear you. Maybe there's a problem on my side. Can we get a no? There's no sound. Also in chat, they're saying no sound.
Maybe you need to check the settings in the Zoom.
There is no sound from his side, I think.
I sometimes have problems. It's next.
We'll figure it out. Worst case, Luca, just you can reconnect to the call, and maybe that's going to help.
Now, no.
Yeah, now we can hear you, but the sound is not the best.
Sound. No.
I think it's going to be okay. So just go ahead.
You think it's going to be okay? So probably when I organized my presentation today, more on demonstrations. So I have here prepared several demonstrations. I'm using, well, I think 4 cameras and also several microphones, so that might be the problem because of switching between all of the systems. So about robot programming, I'm teaching the students in the level 1 and partially in the level 2. They learn the basics of robotic programming. So we have students which come from the technical high schools and the students which come from the gymnasiums, so the general high schools, and they have different basic knowledge. So students from the technical high schools are more practical oriented. Actually, in recent years, the high schools got quite well equipped also with the robots. So many students do have some basic knowledge from the technical high schools, but from the general high schools, from gymnasiums, normally they meet the robot for the first time. So we try to adopt with the courses and tutorials that we offer to their basic knowledge. But yeah, I also realized that sometimes in high schools they don't give equipment to the students because they're afraid that they will break something. But from year to year, I realized that they're getting more and more knowledge, and they're more and more experienced. Anyway, today I will present some basics of manual robotic programming. Then I will present RoboGuide simulation environment. Then we'll go to the vision approaches, vision system, using the integrated AR vision system. We are using the robots from the FANUC company, so all robots and demonstrations will be shown on FANUC equipment. Then I will show you, present how the concept of communication with the FANUC robots is established. And finally, I will present you the RoboRealm example, for example, how we integrate external USB camera with the robot. So in our lab, we have 3 robots. The smallest one, it's a robot that students use mainly for during the tutorials. So it's a robot, it's a small robot, 4 kilos, half meter reach. The second robot, the largest robot, is our, I think, newest one. It has 20 kilos of capacity and its reach is almost 2 meters. And the third robot is a collaborative robot, which is in the middle of the. It can carry 7 kilos and its maximum reach is 700 millimeters. All the robots have the same or even similar controller. So if the students learn how to use one controller, or they can learn the robot usage at the same time on all 3 robots. So how do we learn? Okay, these are some pictures of our robotic cell. So this is the largest robot. So the cell, the concept of the cell is like this. So the one conveyor belt brings the part into the robotic cell. The robot picks the part, places it on a CNC machine. Then the CNC machine machines something, and then the robot picks and places to the second conveyor belt. So that was the idea when we bought the robotic cell, and the PLC controller controls the system. This setup is more used for the research purposes and for the thesis for the students in the final years. The robot is a 6-axis, so all industrial robots are 6-axis, but the controller typically enables to add additional 2 axes. And here you can see also the rotation table for the 7th and 8th axis. This equipment is quite new. We got it just before the Corona started, so we still have to, so in the future we'll be working on this equipment. So this cell, you already know it. So this is the cell that students work on it during tutorials. So the green robot is the collaborative robot. So what is the difference of the collaborative robot? So it has a force sensor in the bottom of the robot, which controls the forces, and if the forces are too high, the robot automatically stops. And this robot doesn't need defense around it. Okay, so we are using for the tutorials, I would say now for 4 or 5 years, the smallest robot, which we bought in the beginning. And this was the academic kit, which is used for teaching the students how to use the robots. I would say that in these years, I would say 500 students were using the robot, and we didn't have any problems in terms of damaging the robot. So the kit is really nice, and we leave this. So normally we give the students some basic knowledge, some basic instructions, how to use it, and they come individually, 2 or 3 students at the same time, to work with the robot. So what are the basic functions which enable robustness? I would say it's a system so-called DSC, dual safety check. So this is the system which constantly monitors the position of the robot arm, which should be within some pre-specified box. And if the robot goes outside of that box, the robot automatically stops. When the students use the robot, the maximum speed of the robot is 250 millimeters per second. And this is not so fast, and each axis has integrated force sensor, so the robot stops if the students hit the surface or the part. Normally we use the cylinders the students work with, and also some demonstration parts which we print. For example, the parts which have pre-specified shape. This academic kit, with this academic kit, also the exercises were provided, but these exercises are a bit, maybe they are, I would say there's no 12 topics, but we cover most of the topics during 2 tutorials. So the tutorials are typically in the time slot of 2 hours. And normally we have a manual robotic programming tutorial, the simulation environment, and the vision system. I would say these are the 3 basic tutorials, so which can be made by the students that don't take the courses from robotics, but they can manually go through the tutorials and are able to furthermore work on different kind of topics related to robotics, but not primarily the robotics. For example, the robot can be used only as a positioning system. So this is our cell, which we have here in front of us, which we will be using today in these demonstrations. So I will try to be more not so theoretical, but practically oriented today. So this robot now in front of me. This is the cell. So here in the bottom we have a robot controller. So the students get familiar with the controller. The controller enables allows free operating operating types, so-called T1, T2, and automatic type. In T1, the manual programming with open fence can be executed with the speeds of the robot are less than 250 millimeters per second. In T2, the speeds are 4 meters per second. In an automatic mode, the robotic program can be started with external signal. So this is important when we integrate the cell with a PLC controller, as I explained yesterday. The students get familiar with the teach pendant. So this is a control box controller for manually programming the robot and to move the robot in positions. So the teach-pendant enables movement of the robot in joint coordinate systems and in Cartesian coordinate systems. So it enables setting of and selecting different coordinate systems. The students normally have the problems because due to the safety features. So you have in the teach-pendant, you have a button, free position button, release, first position and second position. So the robots can be moved only in the second position. And yeah, the students have some problems to get used on the teach-pendant. And yeah, this teach-pendant is, so each producer of robots has its own specialties. But yes, we have the FANUC robots. Yeah, the FANUC company is very well supported. They have very good representatives in Slovenia for the Balkan region, and they help us a lot. For example, during these years, once the students, I don't know, even they don't know how they broke the robot operating system, and they had to reinstall the whole system, and nobody knows how they managed to do that. Sometimes they delete some programs which are necessary for normal robot operation. We have a backup, so if something collapses, we upload the backups. Every few years, backup batteries need to be replaced because if the batteries get empty, then the robot loses its positions and the recalibration needs to be again performed. Yeah, these are practically the only maintenance activities that we made in the past. So additionally, we have here 2 cameras installed in the frame of the robot. So the first camera, it's integrated camera. It's a black and white Sony camera, which is analog camera. I would say, it's industrial camera, but not the newest one. That's why we decided to also develop a system which enables us to use external, for example, a web USB camera, which is a color one. So maybe if in the beginning, we will make a short program just to get to get familiar with some of the basic concepts when programming a robot. So I will show you a short demonstration using the robot. So here we have a screen. So now we are connected to the robot controller via Ethernet communication, and we see the screen of a teach-pendant. So whatever I click on the teach-pendant, you also see here, and the camera which shows the robot environment, the robot cell. There's a web interface, and this interface allows access to different models. For example, vision setup will be used later. So I will switch back to the pendant, and maybe just to get the question what the students do in this tutorial. So I have here teach pendant, and whatever I will click on the teach pendant, you will see on the screen, and we'll make a short program just to get impression. So we have pre-programmed several macros which enable a movement of the automatic movement of the robot in pre-programmed positions. For example, this is the home position. Okay, maybe the camera should be a little bit higher. Okay, Then we have also the 0 position, and in 0 position, the robot is positioned pointing in horizontal direction. So all this, what we are doing today, the students also make on their own. Okay, we'll make a new robotic program. So mostly, the biggest problem for the students is how to learn as fast as possible, how to move how to navigate in the pitch pendant in the controller. And the focus is, of course, on to show them, to learn them how to use the pitch pendant and how to navigate. They have pre-prepared tutorial materials so that they know exactly what to click when. And they have also pre-prepared videos, actually similar, but more in detail as we are doing now. So we'll make now the simple robotic program. We will create a new program. I will call it, I have to name it, which, so this is now the empty program. And when programming the robot, so the first thing is to define the coordinate systems. So the students get familiar with the following concepts. So first is the coordinate system world, which is a Cartesian coordinate system. Which is located in the second axis. Then there's a tool center point. So the tool center point is coordinate located in the gripper, and the students learn how to define the tool center point. For example, in a case when you have a two-position gripper. Then the students also make user frame. So the coordinate system can move wherever you want. So on inclined surfaces, or wherever you want in the robot operation area. And the students manually do this procedure. So when we start programming, we have to define the coordinate systems. And so, as I already explained, the first one is user frame, which is in this case number 1. There can be 2 user frames, 10 predefined user frames, or even tool frames. So I selected now the user frame, tool frame number 1, which are the default user frames. So the user frame is now located, it's a world user frame located in the second axis of the robot. And the user tool is number 1, which is located at the end of the gripper. So you can check the position of the tool center point relative to the selected world frame in this case, and these are the coordinates of the current location. Okay, now let's go back to the program. So when programming the robot, we manually program it by clicking points and manually moving the robot in particular points. And let's say this is our first point. So predefined are four the types of points. So as you can see, there's a difference between J and L. So J means that the robot will go with joint movement type as linear movement type. You can in joint movement type, you can select speed in percentage and in millimeters in linear movement type. Maybe the find parameter, in case of find, the robot gets to the point, it stops there before it continues the movement, and in the case of CNT, the robot goes around the point. So the higher the CNT values, the faster and the more the radius is larger. Let's say we will initially use the find type of movement. I have selected now the world coordinate system, and I will move now the robot in the world coordinate system, and we'll make a simple square. And I'm clicking now the points. Okay, let's move it also in the Z direction. And go back, let's say, to the initial position. So maybe this is our initial robotic program. And you can move the robot to just line by line if the step function is enabled. And now I'm executing the robotic program. So now, as you can see already, so we have an error. This is a very typical error when the students are programming the robots. So as you can see, I always try so that the students are careful when selecting the right user frame, tool frame. So the problem is, it is a very typical problem that we were using the user frame number 8 when we stored the points, but the students, we in the program we are using the user frame 1 and user tool also 1. So we don't have the only option is to delete the stored point and repeat the procedure. So now we will check again if we have now the right coordinate system selected, and now we have the user and the tool, it's number 1. I will again store some points, but this time I hope the right coordinate system is selected. Like this. And I will again move the robot in several positions and store the points. And I will now move the robot back to the initial position. I have to abort the program. And let's say the first position is going to be the same as the last position. And we will store now this position. I'm checking again that the user frame and tool frame are selected the right one. So now let's try the program. So the robot moves to the line by line. So the students go firstly line by line, and then they try to optimize the robotic program. So how to optimize the robotic program? Of course, to increase the speeds, or to change the linear movement types to the joint movement types. It's not always possible to and allowed to use joint movement types, which are typically a little bit faster. but just to have an impression. So the point 3 is now joint type. So we'll check. I will show you what does it mean, the joint movement type. So this point is now the joint movement type. We didn't see yet. I will disable the step and we will make the robotic program to move. Okay. Yeah, we have an error. We have to change from fine to CNT, and let's say 100%. So the point 3 is now changed to the CNT. I'm not sure if it was very clear. Yes, I'm not sure. I think we have to increase the speeds to make it really clear, or at least a little bit more clear. So the main point is that the robot doesn't stop in that point. You probably saw this, and normally the programs are faster if you are using so the CNT point type. So these are now the speeds of the robot in T1. However, we can increase, of course, the speeds can go to 4,000 meters per second. And the students also, yeah, they get impressed with the robot speeds if they try higher speeds. So if I use the T2, if I close the fence, then we can test the robot movements in T2. But as you can see, the speed automatically decreased to 5%. I will now increase the speed to 30%. So 30% from 2 meters per second. It's, let's say, 700 millimeters per second, which is already quite fast. And, yeah, I see the camera has some problems. Yeah. The camera has problems because the fence is closed now. So for the last time, yeah. But the robot is extremely fast, so I feel safer because the doors are open. So we'll go back now to T1, and I will switch now to show you some other demonstrators. Just a second. So then the students learn some more advanced programming concepts. So I give them different tasks. For example, in this case, the task is to develop an application, robotic program, which picks the cylinders in one location, and then it makes a tower of cylinders. So the students learn what is a register, and how to use the register, how the for loop is implemented in the robotic program, and how to call programs. Additionally, they also use the position register. So the position register stores 6 positions, so X, Y, Z, so 3 rotations and 3 translations, and each of the registers can be, each axis can be individually stored. and the students need to understand how to use the position register. So I will switch back to the demonstration, but in this case, we'll just run the program. The program is called automation. This program. Just a second. Okay, I have a really similar name of the program. So this one is the right program. So the robot picks the cylinders from the hole and it makes a tower of cylinders. I have to increase the speed. Okay. Of course, we give the students the variations of this type of program, let's say to pick and place along x-axis, y-axis. Maybe the tower is quite interesting because typically they compete to make the highest. So as I said, these tests are also made by each of the groups which come individually to train the program. Okay, so that was the programming example. Now we'll go on. So basically, this is the first tutorial. And the second tutorial is about RoboGuide software. The RoboGuide software is a simulation environment which was provided by the FANUC. And we got 20 licenses when we got this academic kit. So we are typically using 10 laptops, and the students do use the RoboGuide to make a demonstration simulation example. So the purpose is to learn how to make a simulation, how to make a pick and place simulation. They go for a simple tutorial, and finally the simulation is actually a digital twin. So when they make the simulation, they put the robotic program to the real robot. Just to show you the final, the final result of this tutorial. So it's a robotic program. The robotic program is simulated. So they make the simulation. Sometimes, the same instructions that I showed you before are also used in the simulation. So they have to do it in the right way. So if they make some mistakes, then the robotic program will hit the part. The software also enables the simulation of the cycle times. which is interesting. So when you make a real industrial project, you initially start with the simulation, and so the simulations are maybe not so interesting for students because they maybe it's more important for them to work on the real equipment. But to get familiar with this tool, I think it's still okay. The robotic program can be stored as a text file or binary file. So the binary file looks like this. Just a second. The binary file. So sorry, the binary file can be read, but this is this is just to get impression how does it look the file robotic program when exported from the RoboGuide. So this is the file. So you probably already now understand, as you can see, we have selections of user frame, tool frame, and then points. And the procedure is actually the same throughout the program. And each point has also predefined, so this is point 1, coordinates. So you can understand that. So this is only the robotic program could be used also as a CNC program with a short translation and with the selection of a right post processor. So the program can be changed here or later directly on the robot. Okay, I will show you. I will demonstrate you now this program in the real robot. Maybe before we continue, there's also a teach pendant functionality in the RoboGuide, and sometimes some students do like the teach pendant, and they learn the usage of the robot also through the teach pendant. So if we select the coordinate system, let's say joint, the robot is moved around first axis and so on. So the teach pendant is the same as the real teach pendant. So I would say quite interesting. So as I promised, I will show you now the robotic program. It takes place a robotic program from the simulation environment. So we'll go now to the program. Just a second. So I selected now the simulation program. And in this case, the robot picks the part in one hole, and it moves it to the second hole. And this program was simulated and then transferred from the robot. Okay, next I will go to the camera part of the demonstrations. So as I explained before, we have two cameras. One camera is the analog camera, which is integrated camera. And this is again, a new tutorial. And so the main purpose is to learn how to use the camera with the robot, which needs to calibration of the image. Then the coordinate system needs to be integrated. And finally, the student make the robotic program to pick randomly positioned parts on the machine table and to place it in an organized way. So the procedure for this integration is like this. Firstly, the students have to define the user coordinate system. And this coordinate system is the integration point for the camera and for the robot. So here on the robot, you can see a point, a tip, or a pencil, and this tool is then moved to the predefined positions. So this procedure is predefined by the FANUC company. So in this case, the origin of the user frame is in the middle. As you can see, the calibration body, it's a pattern, it's a grid pattern, which does not consist only of dots, but also of this special L in the middle. So this L enables definition of the orientation of the user frame. Then the students go through several steps. In the ER vision, they calibrate then the camera. They learn how to set the exposure and the lighting conditions. The lighting conditions are maybe one of the most important part of the parameter when using the cameras. They select then the right user frame, and finally the calibration pattern enables then the calibration of the camera. And typically, so the camera is around 1.5 meters away from the table. The deviation of the calibrated points are less than 1 millimeter, or typically 0.2 millimeters. And for each point, you can check the deviation. So now the camera is calibrated, and in the next part, the task, the camera task is defined. So the camera can, the vision process can measure the dimensions of the part or just the positions of the part. In this example, the students measure with the camera the position and orientation of the parts in the predefined user frame. And in the first step, you have to learn the system, what is the part that you want to pick, and which are the features on the part which define the position, orientation of the part. So these are the parameters which enable the selection of the part. There are some specific parameters. Let's say you can define, so the system automatically defines the edge of the part, and what is the edge, the parameters can be changed and set. So the special parts on the part can be masked, and faces area on the part can be also defined. So all these features and settings enable more precise definition of the center pickup center point, the location definition. because to successfully pick up this part, the center really needs to be within several millimeters in the middle of the white area. Otherwise, the robot will hit the part. So, but of course, you have a problem because the parts have some height, but they are calibrated directly on the table. So we have some problems with perspective, especially if the parts are located far away from the center. So then they have to define the initial orientation of the reference part and also the location of the reference part. Typically, I prefer to set the location of the reference part in the origin of the user frame, since it's easier to debug, to solve some problems in the program, especially if the problems are in the integration aspects of the user frames and calibrations. So if the part is then successfully found on the table, so then the image is not, the part is not located in the pixels, but in the millimeters. So in the user frame of the predefined robot coordinate system. So in this example, you can see, in this case, you can see that the center of the third part was not successfully defined. So how to solve these problems? For example, yeah, it's not so easy because it's really important that the threshold levels, black and white areas, are really clear. And in this particular part, this was a problem. And later we made a new part. So in the robot, we have a vision register in which the positions of the part are stored. And finally, the students then make a robotic program to pick and place the parts which are found on the table with the vision system. So in this case, you see the part is, this program runs the vision process, and which finds the parts and then stores the positions of each part in the vision register. So if the vision register if the vision process doesn't find parts, then the program jumps to the end of the program. Okay, again, I have a demonstration of this system. So now we will put black and white, which are positioned somewhere in the middle of the table, and the robot will pick the parts and place them along x-axis. So as you can see, the black part is so the vision process finds the center of the black part of the cylinder. And again, I will find the program, which is called Hammer. Just a second. Okay, this one. So we won't go now into details about the vision system. The profile is pretty was already prepared. So the robot firstly moves away from the away from camera, then the camera images the table, and the vision process is then executed, and parts are stored into the vision register. Maybe the program is not the best. There are some rotations. Okay, I have some problem because as you can see, the robot moved to the edge of the area, and the robot, the DST function stopped the robot. Because I know from the yesterday what is the wrong, we will fix the error. So there's some error in the position register, which moved the part too far away. Okay. 1 minus. I hope now it's going to work. We slow down a bit. Okay. So this way, so this is also the task for the students, but I would say that maybe half or 2/3 of the students are successful in solving this tutorial, but maybe 1/3 they have big problems. These tutorials, because there are many small details, and the tutorial is not successfully finished. So this is now the vision, and maybe the last. Now we will go to the last demonstration, which is about usage of the external USB camera. So this camera is located in top. So it's classical camera. Not much better, but anyway. So we will be using for the image processing the software called RoboRealm. So this software enables processing of images from camera the same way or similar way as the ER vision system. The RoboRealm software for personal use is 50 euros. Oh, I wasn't, so I have a personal license, but I'm not sure what is the license price fee for the academic. I think there's also academic license, but I'm not sure what all is included in the academic license. Professor Bretschun, I think he has academic licenses, but as you can see, also the commercial license, it's probably quite price competitive for some specific tasks, of course. So here I have now the RoboRealm software, and this is, I hope, the live image from the body camera. And this is a simple a simple program for image analysis. So how does it work? So these are the functions which you drag and drop from the drop-down menus on the left side, and then the software executes the functions. So if you are with the cursor, for example, in the third line, and then I click run, then the software automatically is executed till the third line. So in this case, we'll be working with the red color cylinders. But before we go to this demo, I will switch back to the final part. Yeah, to this part. It's about how to communicate with FANUC robots. For example, if you want to read or write input and outputs. From the usage perspective, we have we read or write inputs by using the HTTP requests or queries. So with the curl program, and if you execute this line, you get the result. So in this case, we read the value of the input 2, and the input had the value 1. The similar way, we also write the outputs. And maybe the most important is this way we can also store the position values in the robot in the position register. So we can so in this case, if we execute this query, we store the position X, Y, and Z in the position register, I think 80 or 81. How do we program in this type of programs, which are so-called curl programs? We again use the RoboGuide software. And we program so-called curl programs. Normally the students don't do this, but maybe for some seminars, to solve some specific tasks, they have to dive into the curl programming, which enable, of course, programming more advanced functionalities. This type of writing to the position register enables, for example, 10 times per second the writing in the position register. And at the same time, of course, the program can then move so many times. But from my experience, the robot cannot, from the mechanical perspective, it cannot move so many times per second, especially if the movements are really short, which results in high vibrations. So for many applications, 10 times per second in this approach can be used for integration with external systems. So this string needs to be calculated and executed from the RoboAlarm software. And now we switch back to the RoboAlarm. So in RoboAlarm, again, the will be executed. Body for RoboAlarm. So you have to be careful when selecting the frame rate or the output size of the image, because this can drastically affect the integration of coordinate systems. And then the next function, with this function we crop the area. So we will look only the middle part of the table. So the RGB filter is used to filter only the red, to mask and to filter only the red pixels. So these are, so because now I have only one cylinder, So as you can see here, it's really important that cylinders are nicely colored. Otherwise, they're not cylindrical shape, and because later we try to identify the center of the cylinders, we'll have problems in defining the center. So then we have a blob filter command. So this command filters only the blobs which are in pre-specified range, and it stores the positions of the blob centers in the array variable. The array variable is then manipulated with a Visual Basic script program. So the main purpose of this script is to integrate the coordinate systems. So we need to scale the image to transform it from pixels to millimeters, and to translate, and we don't rotate the image, and these functions are realized. So for each calculated center of the blob, and therefore the cylinder, the center is calculated in the user frame of the robot coordinate system. So, the center, this rocket in the middle, this is the center of the user frame. And this is the coordinate. So maybe the hardest part of this tutorial is to be really precise when calculating these transformations. Just a second. Okay, so now here we can see now the position of the part. I will place only one part on the machine table, so on the robot table, and this way you can check if you move the part into 0 or around 0 of the defined user frame. So here you can now check if everything works correctly. So now we are 80 and 90, and I think it's more or less really in that position on the robot table. Okay. Now these coordinates need to be written to the text file. Second, to the text file. So you already know this string. These are the coordinates, and then the program is at the end it's executed, and if everything works as it should, then we have, so now the program is being executed. So if I move the part, so it's going to, it's moved, and the position of the part is stored into the position register. So now we'll go back to the robot controller, and we'll check now the position register, which is number sorry, it's not position register, but it's just a register because it's sorry, it is position register number 81. So here, if we check the position register values, you will see that the position registers are constantly changed, but only, as you can see, less than 1/10 of millimeters. So there is a little noise, but not so big. So we'll go now back to the main program. And we'll check now the main program. I think it's this one. So in this program, the values from position registers are stored in another position register number 7. Again, we have a for loop which executes 4 times. And again, the robot moves to the above the cylinders and then picks and places again in the, I think, to build the tower. Yes, I think so. Okay, so to finish this presentation, okay, I will demonstrate also this program. As you can see, we have some problems. In centering the part, but we are still, I think we are at least 5 millimeters shifting in the last part. Looks like I wasn't careful enough. So, he did try twice, but unsuccessful. So this tutorial, it's typically more for the seminar world. This year, the students didn't do this tutorial, but I think in the future, this type of the tutorial, because it enables integration of the robot with different type of cameras, of course, it will be developing into the future. Especially the beam picking functions and projects are getting more and more important, and Professor Brachun bought a new camera which enables instant picturing of the parts on the machine table, and we will be using this semester with the students this new camera. So to the end, the robotics is constantly changing, and we have to be always with the time. And these tutorials that I showed you today, in a few years, they will be, of course, completely different. So thank you very much for attention, and I'm free for your questions.
Thank you, Luca. Yeah, so again, a very nice practical presentation of how we do the teaching with the equipment that we have. So questions, welcome.
Maybe then I have questions for you. How do you teach robotics in this level in your countries?
Not sure whether there's anyone who's particularly. Oh yeah, hi, hello. Sorry, you're muted.
You're muted.
Oh, hello.
Hello.
Okay, thank you very much for your presentation. Actually, it was interesting related to the real programming. Actually, in our university, we don't have a robot in this form. So we just have small robotics for students in the laboratory. We don't have a big robot to make learning. However, during my PhD in Istanbul Technical University, we have a big robot from ABB company. So the tool for programming, it was from handset or from using a PC computer. From your side, is it possible to connect this robot to any simulation program or real time like LabVIEW or MATLAB, or just special software from the company same?
So this last example, I think it's the most that can be used to integrate it with LabVIEW. We didn't do it yet, but I don't see any problems or any other software. So I think this is quite a general approach, which is predefined by the FANUC company. So how to integrate it with other softwares. But I saw that for the Sprut Cam, so this robot, there is a post processor for all of these FANUC robots, at least as I know.
Okay. For this software also, you check the repeatability and reachability for this like factor to check the quality of the programming or for the robot. I mean, you check this issue or just pick and place. So if I repeat the task for 10 or 100, 200, so I will have the same. Did you test such kind of thing?
I know that for ER Vision, there are modules specialized for checking the dimensions. I admit I didn't use it yet. Not sure for RoboRealm, but I think yes, it also allows this type of modules to measure dimensions. But as Rock explained in the morning, the C++ is the right way for this type of tasks.
Thank you very much for your presentation, by the way.
Yeah, thank you.
Thank you.
Okay, thank you. Do we have any other questions at the moment?
Thank you.
Okay, so
thank you. Yeah.
There don't seem to be any other questions at the moment. So thanks again, Luca, for the presentation. I'm posting the links for the evaluation of the trainings in the chat again, just so we get the administrative part over. But anyway, I think both Luca and I are very open. If you have any other questions, just send us an email. We'll be happy to work together if there's an opportunity. If an opportunity arises, for sure.
Our pleasure.
So yeah, thank you very much.
Thank you very much for this.
So thank you, Luca, again for the presentation, and we'll continue in about 1:40 with the topic of the robot operating system presented by Andrea. So thank you, Luca.
Thank you.
Thank you. Bye-bye.
Bye-bye.